Let's start. Okay, so let's remember where we were last time. We were discussing modular invariance of the superstring of type 2a and type 2b theory, and we'd gone through this slightly painful discussion where we defined these z alpha betas. Right? You remember them? They were, and now I'm going to use the fact that we always, in the end, use Polchinski's conventions. So I'll take the definitions from Polchinski, so we don't have to do it again. It was trace adjustment. Yeah, alpha adjustment. Yeah, the first guy, the space guy, had periodicity psi of 2 pi is equal to psi of sigma times psi of 0, thank you, times e to the power I pi alpha, I pi 1 minus alpha. Okay, so this alpha was the spatial periodicity, and the beta was presumably just trace e to the power I beta f, right? I pi beta, I pi beta, that q charge. So, yeah, and we're computing trace e to the power I pi beta q such that right, this q charge was such that minus 1 to the power f was equal to e to the power I pi q. Okay, and so that beta equals 1 becomes a factor of minus 1 to the power f. Okay, so these were the things that we were computing, and then we got an explicit formula for these z alpha betas. Okay, this explicit formula, which we calculated last time, was 3 alpha squared minus 1 divided by 24. Okay, and e to the power I pi alpha beta by 2, and then some oscillator stuff which I'm not writing. Okay, the important thing about the oscillator stuff was a function of q to integer powers, or q to half integer powers, right? Depending on where this one? No, this just came from the charge of the vacuum. So it came from this term. Okay, so it was just a phase coming from that term. Okay, now the important point is the following. Okay, we also argued last time that what we got for the partition function of type 2a or type 2b theory, I mean, we're looking at either side. Right? We're doing the left movers and right movers separately. So either the projection with either of the two projections. The only real physical difference is whether we used the same or one and the different one on that side. But just as a mathematical statement, the two different projections were half z0 0 tau to the power 4 minus z01 tau to the power 4. Okay, minus z10 tau to the power 4 minus plus z11 tau to the power 4. This was the partition function that we said that we would try to, we said we would try to check was modular invariant. Okay, And I'll just quickly remind you where each of these terms were, what each of these was in terms of diagrams.
This partition function was for generic alpha beta, and then this for special case of Raman there are degeneracies, and then you need to tell me which ground state you are taking.
No, I'm doing the partition function. So the partition function will include both ground states.
Okay, so this the answer that is written above.
Yes.
For arbitrary values of alpha, there will be no degeneracies.
There'll be no degeneracies, but we put the particular values of alpha and you'll see those degeneracies.
And then this.
That's because, you know.
Take into account separately.
What?
Right?
Say again?
If you have two degenerate ground states, then you have to take into those two cases separately.
No, it's automatic. It's automatic.
This is automatically have that.
This is automatic in the whole thing. It will come from the alpha goes to 0 limit. Because you know what will happen is that one of the oscillators will have almost 0 energy.
Okay.
And that will give you the ground state degeneracy. Okay. And there's nothing singular about that because these are fermions. So instead of contributing 1 plus q to something very small, contribute 2. Yeah. So it's just, it'll be automatic. There's nothing, you know, when bosons have 0 energy states, something singular can start happening.
Yeah, many things consider something like that.
What? You can get an infinity.
Many states,
Many things, yes. When fermions have 0 energy states, something singular can also start happening if you're computing, the wrong trace. I mean, you can just get 0. If you're computing trace minus 1 to the power f. Because the two states cancel and give you 0. And indeed, that's what will happen here. Because then we're in the Raman sector and we're computing with trace minus 1 to the power f.
Yes.
And so this will just be 0 because of the cancellations. Okay? But nothing singular is happening.
That's automatic. Okay.
Yeah.
Where's the power of 4 coming from?
The power of 4 is coming, if you remember, we took our fermions and grouped them into pairs of 2 to get one of each of these z's. And there were 8 fermions. Okay? Because we were doing this light cone kind of thing. We promised to do it more carefully including the ghosts and all later. At the moment, we're just doing light cone. Okay? All clear? Okay, excellent. And okay, I'll just remind you what all of these things were. Let's set this guy 0. So that was alpha. So that means, according to this formula, yes, the fermions were anti-periodic in space, which was the Nebuchadnezzar sector. Okay, so we write this as minus in space, and then we said beta 0, this guy 0, which was no minus 1 to the f projection, because we were going to put a up here, what, and therefore anti-periodic in that. Okay. Now this guy has the same thing in space, so it's also minus, but it's opposite in time, and therefore with a plus. So this thing together was trace of 1 minus 1 to the power f by 2 in the ns sector. The minus was because we were doing the light cone. So this is just the GSO projection in the light cone, because you remember the ghost sector automatically had minus 1 to the power f is equal to minus 1. Okay? So this is just the GSO projected NS sector. This guy was a little weirder, and it's a little weirder because of the negative sign. So let's take out the negative sign and remember what it was. Okay? So, yeah. So how did this go? So now these two, which are the spatial directions, tell you that you've got positive periodicities in space. Right? Because we said alpha equals 1, psi of 2 pi, psi of 0. So we're in the Raman sector, but first we'll write it like this. So plus and plus. Now we get an overall minus, and then we've got a plus minus here. Okay? This guy is, this guy is what this was. So it was minus, and this guy was plus. Okay? So this is the same thing as trace in the Raman sector 1 plus minus minus 1 to the power f divided by 2. But there is this minus here. Okay? So what we're doing to get our partition function is taking the projected partition function in the NS sector. This is exactly what you would expect. But in order to get modular invariance, we need to take the projected partition function in the Raman sector with either the plus or the minus. This is the type 2A or type 2B projection. That's what we expected. But there's an overall minus sign. Okay? And at first, this sounds really weird. It sounds like we're counting states wrong. Okay? And the reason that this is happening, but it's not weird actually when you think about it. Because you see what this torus doing, the simplest torus diagram, as we will study as soon as we end the formalism part and start doing physics. The simplest torus diagram in this whole game is the vacuum torus amplitude. A torus amplitude with no insertions, no vertex operator insertions. Okay? Now what is that? What is that string world sheet? It's this donut string world sheet. Actually, everything I'm saying also applies with vertex operator insertions. Let me say it in this context, and when we come back to. Okay, now you see, what is this thing? From the point of view of field theory, of quantum field theory, what this is one loop graph. Because you've got this little string, each oscillator state of the little string is a particle, and it's going around in a loop. It's a one loop graph over all of the spectrum of the string. Now, where do we get this one loop graph from? It's just that this one loop graph, this bubble graph, not even a one loop, it's sort of like a bubble, is simply a representation of the determinant. Okay? And we know that the right answer for vacuum amplitudes in quantum field theory is that bosons contribute determinants, but fermions contribute inverse determinants. Okay? So once we take it to the exponent, if bosons come with a positive sign, fermions should come with a negative sign. There's a similar statement for every Feynman graph. Suppose we had something like this. These would represent one loop contributions with external states coming, creating one loop contribution. And once again we know, you know from Peskin and Schroeder, that it's part of the rules, the Feynman rules, that every fermionic loop picks up a minus sign. Okay, it's the same minus sign. So if we want string theory to mimic even the gross features of quantum field theory, it had better be true that when we have a loop, bosons running around in the loop and fermions running around in the loop should contribute oppositely. That's how it's going to reproduce the right space-time partition function. That's how it's going to reproduce the right Feynman graphs. Okay? So notice that, you see, if we were thinking of this as the partition function of the world sheet theory, it's not the right thing in some sense. It's a weird thing. But that's not what we want to compute. Right? Because this would be like a ghost type partition function. Because these states are contributing negative, whereas these states are contributing positive. Okay? So in some sense, it's not really the partition function of the world sheet theory that we're computing here. But it's the thing that we want to compute. Namely, it's partition function weighted with minus 1 to the power f space-time. Okay? Because that's the thing that we are interested in doing. Now, what is f space-time? You see, f space-time, because of spin statistics theorem, you keep track of in the following way. Every time you have a spinorial representation in space-time, you count that as minus 1. Every time you have a vectorial representation in space-time, you count that as plus 1. And then you're bound to land on your feet, because an even number of spinorial representations will always be a vectorial representation, and therefore will be a boson. An odd number of spinorial representations will always be a spinorial representation, therefore it will be a fermion. Okay? So now we know that because of the degeneracy that Indranil was talking about right at the beginning of the class.
Did you mean fermion number 0 for vectorial, or?
Did I say the opposite? Yes. That's
No, I mean, you said -1 +1. I mean, one should be 0 and other should be.
what in this graph here?
No. In terms of the fermion number, the assignment of fermion numbers to vectorial and spinorial representation.
Yeah, fermion numbers are either +1 or -1. Sorry, I mean whether the contribution is full.
the -1 to the f.
-1 to the f. Right. That's right. That's right. Sorry.
That.
Yeah, just whether it
Yeah.
contributes plus or minus in this
Yeah.
graph. Okay. So you see, we're going to do the right thing because any number of additional oscillators in the NS sector will not change whether it's fermionic or not. Okay, but each state in the Ramon sector is automatically spinorial because of the quantization of the zero modes. Okay, so if we do this and then we square it because we've got one on the left and one on the right, it's going to work. Because either we have two states in the NS sectors, those are clearly bosonic, or we have two states in the Ramon sector, those are bosonic, so should contribute with a plus, but they do contribute with a plus because the two minuses cancel. But if we have one thing from NS sector and one from Ramon sector, then we wanted to contribute with the minus because those are going to be fermions in space-time, and they do contribute with the minus. Okay? So at first when you encounter this, you think you're doing something wrong. Because you're somehow prejudiced. You think I should be putting the world sheet partition function. But if you think what you're actually going to use it for in space-time, you don't want the world sheet partition function, you want it after some signs. And precisely those signs, with those signs, the whole thing's going to turn out to be modular invariant. Okay? So if you were foresighted, this is what you would have expected. And then you would have seen, this is the thing that's going to be good. Is this point clear? It's an important physical point.
Fermions are space-time vectors, so those case our operators didn't change anything.
What? Say again?
Fermions are space-time vectors.
Yeah. So indices of the fermion do nothing.
So therefore their case annihilation operator did not change.
That did not change anything. It's only the zero modes, quantization of the zero modes that give you spinners. It's the only source of spinners in the problem. Right. Every explicit index in the problem is a vector index. And so from this you might have thought we'll never get spinners. Unless you get zero modes. There's a way out by quantizing zero modes. It's the fact, right, that gamma matrices are vectors, but their quantization, the Hilbert space that they act on, is a spinorial Hilbert space. It's this fact that's being used. Okay, is this clear? Okay. Now let's move on to the part that we were talking about right at the end of our last lecture. Okay, and that was the question of whether this thing was modular invariant or not. Naively, it's modular invariant. Why is this? Okay, let's look at it under flip.
Last time when we had an argument similar to this, the argument we would have made is that the first three terms would have to come with the same sign.
Last time we had an argument similar to this. You see, let's look at first under flip. We're going to get anomalous signs in 2 minutes under tau goes to tau plus 1. Okay. That's what will mix the first three terms completely. Okay? But first let's look at it under flip, under the S duality. Under S duality, this guy goes to itself. That's just changing the space and time cycles. These two guys are interchanged. Okay? And so the fact that this came with a minus happily maps to the fact that this comes with a minus. Nowadays it's the minus that is non-negotiable. This guy, whether by type 2a or type 2b, flips. Okay? So these two signs being the same was necessary for S duality. And S duality turns out to be the uncomplicated part of this modular invariance. But there is no funny signs. All the funny signs come in the tau goes to tau plus 1 transformation. Okay? This guy, of course, under flip is invariant. Okay? You can see it more clearly from the diagrams, I suppose. So this was plus plus, this is minus minus. These two interchange. Okay? And they both came with a minus, as we see. Okay? Now let's get to Yankee's question. Yankee's question was, okay, well, looks like it's working okay for the S, but it doesn't look like it's working for the T. Tau goes to tau plus 1. And let me give you Yankee's, the argument that he, I think, has in mind. The argument he has in mind is that, look, suppose I go to this cycle, then this guy becomes plus minus. Okay? So that's what tau goes to tau plus 1 will do. But it looks wrong because this guy came with a plus and this guy came with a minus. So it looks like, despite all my brave reasoning, this object is not modular invariant. Okay? Perhaps, but it's not quite right. Why is it not right? It's not quite right because we are assuming that the modular transformation properties of this are the naive modular transformation properties. Okay? And they're not precisely because of this term. Okay? So, let me say what I mean. You see, under this modular transformation, this transformation that tau goes to tau plus 1, minus minus will go to plus minus, but will also pick up an additional phase. It's, if you want, an anomaly. It's the same kind of thing that, it comes from the fact that we've taken left movers and we're dealing with them separately from right movers.
Why is it that term that picks up a phase and the next one?
The next one is everything good.
The alpha beta, right?
Ah, it's because there's no q in that. But in tau goes to tau plus 1, it's q that's shifting. Okay, q is shifting by q goes to q times e to the power 2 pi I.
Whatever the argument.
Okay, so because this is not an integer power, this picks up a phase. Now you see that this phase clearly has nothing to do with changing the moding of oscillators. Okay, it's just an overall phase coming from the ground state energy. It's the same. It's in the same spirit that the following is true. You know that in a partition function, under tau goes to tau plus 1, if the partition function was otherwise invariant, you would anyway pick up a phase, and that phase would be L0 minus L0 bar. Because we have e to the power 2 pi I tau times L0 times e to the power minus 2 pi I tau bar times L0 bar. That's the trace we're taking. Now under tau goes to tau plus 1, you pick up the eigenvalues of L0 minus L0 bar. So, had there been no complications of period, had we been dealing with some theory where we didn't have to keep, where tau goes to tau plus 1 didn't also shift pluses and minuses, which is the case at this point, but just put that out of your mind for a moment. Okay? Had it been otherwise invariant in the sense of pluses and minuses. Okay, so for instance in the plus sect.
This was the rotation one, right? Rotation operator.
Exactly, rotation operator.
Is it not going to return that 2 pi rotation is not identity?
Right, exactly. This because L0 minus L0 bar is the angular momentum.
This 2 pi rotation in space is not identity operator.
Is not identity unless you have angular momentum eigenvalues being integers. So this will pick up e to the power 2 pi I L0 minus L0 bar. And unless L0 minus L0 bar is an integer, a 2 pi rotation will not bring you back to yourself. Okay? But would bring you back to some phase. So in a situation, if you had such a situation where you're left moving ground state and your right moving ground state, they had a different L0 ground state energy from L0 bar ground state energy. Okay? The whole thing was otherwise modular, otherwise fine. All the oscillators were doing whatever they were supposed to be doing. But the left moving ground state energy was removed from the right moving ground state energy by some strange amount. This thing would pick up a phase under tau goes to tau minus 1.
So the level matching we had was only for oscillators?
The level, no, the actual level matching in the full theory is going to work very nicely. But we're just doing this bit by bit. Right now, forget about, at the moment, look, we've got only left movers. Yeah. Sorry, I maybe shouldn't have said this. This maybe is confusing. You can forget about this for a moment. Just go back here.
We're just looking at just the fermions.
Just fermions, just left movers. Okay, we're just doing some algebra. We're looking at just left movers, just fermions, and we're trying to see what this is. Now, the point is that this part, you can easily check from the oscillator map. If you go to tau goes to tau plus 1, the oscillator part will transform under modular transformations, like this diagram tells you what it should. So this guy will go to this guy if you do tau goes to tau plus 1. This is something easy to check. Okay, there was an explicit oscillator algebra, oscillator thing, and you just do tau goes to tau plus 1 in that. Okay, the point is that you have some half integers. So tau goes to tau plus 1 doesn't do nothing. Right, you have q to the power integers and half integers in the oscillator stuff because that's the NS sector. Okay, so tau goes to tau plus 1 doesn't act as identity, it does something, but it just moves you to this guy. I'll leave that as an exercise for you. It's a trivial check. Maybe you've got the explicit expression, just check.
So if you have multiplied the anti-holomorphic parts as well, then this will not happen, you are saying?
Well,
For arbitrary alpha beta?
no, you see, what we want to do, what we are doing now is about relative signs.
Yes, so that will be this times the anti-holomorphic part.
The anti-holomorphic part can deal with some overall thing.
Yes, because this part will get multiplied with similar quantity for anti-holomorphic part.
And so overall phases are not important.
Yes, only overall phase can get cancelled because it will multiply.
Apply like that. But the relative phase has to be cancelled within the left moving sector.
Yes.
Okay? So that's what's important here. It's the relative phase. And this is of course what the problem was, right? Yankee pointed out that naively there was an issue with the relative phase. Forgetting about anything overall. Okay? And actually that's not an issue because it's exactly as it should be. So let's check that. Let's take this guy. Okay. So under tau, what do we expect?
I couldn't understand that.
Yes.
Is it that in some sense this tau into tau plus 1 is an anomaly? Like if you can turn on the background gauge field which cares about this global symmetry tau into tau plus 1,
Yes.
then you will see that the partition function is in usual sense the truth anomaly. If it was this, that
I'm writing down exactly what the algebraic claim is, and then we'll discuss the words to it. This is that there's no anomaly in S duality. Okay, but is equal to exponential of minus pi I 3 alpha squared minus 1 by 12 z of alpha plus beta minus 1 tau plus 1. This is the claim. So this part we've already discussed. So let's throw that away from our minds. Okay? This is the important part. Now, the first thing I want to explain to you is that had things been transforming according to geometry, then we would have got this without this term. Okay? Let's look at it. See, suppose we had minus minus. Under tau goes to tau plus 1, of course we would get, this tau plus 1. Okay? But minus minus will go to plus minus. Okay? Now, this minus was alpha, so that's not changed. Okay? So, suppose Whereas this minus should have become a plus. So let's see that it's working in this case. Okay, what was this? This was 0, 0. It should have gone to, we expected it to go to 0, 1. Okay, and that is the same as 0 plus 0 minus 1. Remember, all of these things are mod 1, you know, mod 2. Okay, minus 1 is same as 1. Okay, mod 2, yes. Okay. This, it's basically this point, right? We want to keep track of the overall phase of the fermions as they go across this cycle. Okay, what was the phase of the fermion as they went across here? Okay, it was this one, e to the power I pi minus 1 to the power alpha. What was the phase of the fermions as they went over here? It was e to the power I pi, 1 minus beta. The e to the power I pi was the fact that trace gave you a minus 1 to the f, and then the beta was explicitly put there. Okay, so the whole thing is e to the power I pi, 1 plus 1 minus alpha minus beta. And this now has to be identified with an effective beta. Okay, so the effective beta, so 1 minus beta effective is equal to 1 plus, okay, so 1 minus alpha plus beta minus 1. And therefore, the effective beta is alpha plus beta minus 1. Yes?
Usually when you have tooth anomalies,
Tooth anomalies, yes.
you have a partition function which is non-gauge invariant
Yes.
when you turn on background gauge field.
Yes.
But the failure of gauge invariance satisfies some conditions. Suppose a minimum consistency condition.
Yes.
This phase factor
Yes.
satisfies something analogous to that. That will be like sort of criteria.
Okay, now let's think in what sense this is a tooth anomaly. What is the gauge field for this tooth anomaly? Some Z2 kind of thing.
T square is non, T never squares to identity.
Right.
Like no power of T.
Okay, so you say that you try to put a gauge field for SL2Z somehow.
Yes, and then the field.
Some sort of discrete kind of gauge field. Yeah.
But it's not, the anomaly isn't under the whole gauge group, because we have this gauge group generated by 2 generators and one of them is fine.
Right. So, but that would also come into his formula. His formula would say that the lack of gauge invariance is in this part. Presumably there's some story like this. I think that it must be equivalent to the story that, that the modular group is being represented. It's this co-cycle condition. In quantum mechanics, you're allowed to represent groups not just faithfully, but up to phases.
Yes, projective representations, and then the phases will be different co-cycles that you can get for that particular group.
Exactly, and then there are some constraints on the phases.
Yes.
That are allowed. Okay, that's exactly what will happen here, I think.
So you really think this will be like a tooth?
Yeah, I think so. I think it will be basically they're getting some sort of projective representation. The representation up to phase of SL2, of this SL2Z. I think. I would have to check. I've never checked that, but I think that must be the case.
And this is sort of, if C was 0, still it will come, right?
If what?
If the conformant anomaly was 0 for the system, still this phase will come or not? I'm just trying to understand, is it related to the fact that you already had an anomaly?
No, it is, you're right that it's, it's coming from the ground state energy in some sense.
which cares about C.
which is basically determined by C.
Yes, but if your system was coupled in such a manner, this fermion is coupled with another system, let's say, so that the anomaly is not there,
Right.
then would you still get it? Then this will be a manifestation of something more.
You know, at the moment, all that's happening is something relative. So say you couple something to some extra ghost or something like that. Let me think for a minute.
No, that will, if it is overall, then this
Yeah.
is not going to help you.
It doesn't look like it's going to help unless you're somehow coupling.
And that also not cancelling your anomaly in each part.
No.
So that's not what I want.
Yeah, I don't think so. I think it's just that you're taking a theory and trying to define a partition function for left movers, which you cannot do. You've got some intuition for what should happen here from geometry. And that intuition says that, well, if I've got a torus, I've got a torus. Whether I call this plus minus or this plus minus, it's the same torus. But your regulator depends on your labeling. That you're not able to regulate this in a good way. I think it's that. Yeah. Okay. Excellent. So is this clear to everyone? That had we been doing just naive geometry, or naive path integrals, we would have predicted that under tau goes to tau plus 1, beta goes to 1, beta effective, where beta effective is given by this formula. Is this clear to everyone? Okay. However, it's not.
So now if we look at what happens to this is sort of what would happen to the first diagram, right? For the second diagram, we have its time to actually become a minus.
Which one?
The
Second one.
This one?
that one, right? What would happen to the alpha of that diagram?
Yeah, we're going to check that. Everyone goes exactly the same way.
Okay.
This rule is for every alpha and beta. Okay, but we're going to check now what actually happens. Okay, what actually happens is that you pick up this extra factor. Why do you pick up that extra factor? Well, I told you, right? The oscillators are doing their own thing. The oscillators are behaving like you expect them to behave. You can check that in algebra. It's also sort of clear in logic. Because the oscillators are just half integral moded, they're sort of guaranteed to do the right thing. If you think about it. All the funny stuff is coming from here. Anyway, you can check that. Just some simple algebra. Okay? So all the funny stuff is coming from here, and that clearly gives this quantity. Why does it give that quantity? It gives this quantity because each of these picks up a factor of I pi, and there are 4. Where is my? Each of these picks up a factor of 2 pi I. Right, because q is e to the power 2 pi I tau. So under tau goes to tau plus 1, we get an extra factor of 2 pi I times this object. Okay? And that 2 cancels that 24 and gives you the 12. What?
These are both cases for which alpha is equal to 0.
I didn't sorry, could you say that louder?
The two states that we're mixing now are both cases.
Oh, we'll come to those 2 cases in the moment. This at the moment is an abstract statement. That this Z alpha beta picks up this extra field for every alpha and beta. For every case. Okay, it's just that we're putting this in here and putting a 2 pi I. Is that clear? Now we have to apply it to this case. Okay, so now what we're going to do is to see what this thing actually transforms to. Okay, so let's do it painstakingly. We'll use this formula and carefully do everything. So we start with z00 to the 4 of tau plus minus z01 to the 4 of tau minus z10 to the power 4 of tau minus plus z11 to the power 4 of tau. And then I just plug in this formula. Okay, so let's do it.
Power 4 cancels 12 to 3 and then it will become 3.
Exactly, but let's do it carefully. Okay, so firstly, what does Z00 go to? We've already checked that. That goes to Z01. Okay, of tau plus 1. Everything now is going to be tau plus 1. What we want to check is that this thing at tau is the same as the same thing at tau plus 1 up to maybe some overall phase, which will cancel against the right movers. Let's check that. Okay, so this to the power to the 4, but times the extra phase.
To the minus pi I over 3.
Okay, so exactly. So this was equal to 0. So minus
Plus pi over 3.
Yeah.
Okay, I think this is
exactly. So plus pi I over 3. Correct. So e to the power pi I over 3. Okay, looking pretty strange, but let's keep moving. Okay, now minus. What happens here? Well, let's see. This guy doesn't change. What happens to the 1? Well, we get 1 plus 0 minus 1. So we get 0. Right? 1 plus 0 minus 1. Tau plus 1. And the same phase, let's see. Alpha is the same, so everything's the same. E to the power pi I over 3.
the other things will be executed by the addition of another pi. Yes. I mean, the overall phase is minus e to the pi I over 3, I think.
But let's not flip the relative sign between these two. Oh, maybe.
No, the relative sign.
Oh, it has it.
It's
It
okay.
has it. Yeah. But
It's okay.
yeah. Let me write the whole thing and then we'll see. Okay. Then what about this guy? So this is minus 1. It's not changing the 1, and this becomes 0, as you said.
0 and e to the minus 2 pi I over 3.
This is now, in this case, alpha was 1. Right? So as you say, this was 3 minus 1, so that's 2.
Yes.
So 1 by 6.
Yes.
And then 4 of those. So 2 by 3.
Yeah, e to the minus 2 pi I over 3. Which is minus of e to the pi I over 3.
Okay. And then there is minus
Z11.
minus plus. Minus plus Z11. All this tau plus 1.
Yeah.
Again, e to the power minus 2 pi I by 3.
Yeah.
Okay.
And now,
Works because
yeah, this is e to the minus 2 pi I. This is minus of e to the pi I over 3.
Right.
third term is changing sign.
Third term is changing sign. No. Z1 is.
Pi I by 3 outside.
Yeah, let's take pi I by 3 outside. So this is e to the power pi I by 3.
Minus, let's take minus pi I by 3 out, because that will match with what's inside.
Okay, let's take minus pi.
No, I mean minus.
Minus
before
of.
exponential.
Okay, excellent. So then we get Z00 of tau plus 1 minus Z01 of tau plus 1.
Yes.
And now,
E to the minus 2 pi I.
and this is e to the power minus
Yeah.
Minus
minus pi I, which combines with
minus 3 pi I. Yes, minus pi I. So that's plus Z10.
No, there's another minus.
But there's another minus. Yes, exactly. Z10 tau plus 1.
Yeah.
And then
This, it will be minus plus.
minus plus.
Z11.
Right. Z11 of tau plus 1. Right, minus, and then that minus sign has gone out. I think so, because we get an extra minus sign term, but we took that minus sign out here.
Exactly.
Okay. Okay, thank you for the help. And this is exactly as you guys have pointed out, exactly, this is exactly this quantity up to that overall phase.
The last one, this hierarchy will be a minus initially.
What?
That one.
Last
Yeah.
This?
On the exponential.
On the exponential.
Ah.
Sorry.
Yeah, yeah, thank you. Thank you, thank you, thank you. Okay, so yeah, so you see that it works in a number of different ways. See, the first problem that we started talking about, that this guy and this guy came with opposite signs, that by itself was okay. Because had it been just those two terms, then the whole thing could have flipped by an overall minus. Okay? And that's basically the statement that these two came to the same phase. There was no relative phase between these two terms. But then there would have been an additional problem with this guy. And that was fixed by this additional phase. Okay? So the whole thing being modular invariant under tau goes to tau plus 1 just wouldn't have worked with any overall phase if we didn't have this relative phase between these two guys and these two guys. That relative phase is the key. Okay? The overall phase that we pulled out, okay, we could have pulled out. But it's the relative phase between the first two terms and the next two terms that was somehow key to making the whole thing work. Okay? And it does work, and precisely, everything is fitting together. It works because we had 4 of these guys. If we had 3 of them, it would not have worked. Okay. Now,
The last one sits in isolation, sort of. Right?
what?
The last term, the plus term, sort of sits.
Yes, it sits in isolation, and actually this term by itself is 0. Because it is trace of minus 1 to the power f of the Ramond state. It's this term. It's trace minus 1 to the power f in the Ramond sector. The Ramond sector has degeneracy. Every state comes with its partner with opposite opposite fermion number. So trace minus 1 to the power f in the Ramond sector is just 0. Yeah, so it's true that this is modular invariant by itself. These 3 are modular invariant by themselves. And this is modular invariant by itself. Okay? But you couldn't drop this. You couldn't drop this A because then there wouldn't be a Hilbert space interpretation. Because then you would have the half. Everything here has half. You'd have the half here, but without a partner.
But it looks like that this is sort of a sum. I don't even know if the first one is an irreducible representation, but it looks like a sum of 2 different representations.
Yeah, it is. Actually, you can see that just from the diagrams. Plus, plus. Under modular transformations, it doesn't mix with anything. Right? Suppose fermions are periodic here.
So why can't I look at the Hilbert space of this, the 3-part representation alone?
Well, you can do it in terms of these diagrams, in terms of path integrals.
Right.
But now you ask, does that have a Hilbert space interpretation in terms of traces? Okay? And if you do it with the halves, it does not. Right? This part of this diagram was just this.
Yeah.
It won't give you integers for the other thing. Okay? Yeah, so have this thought of as being the GSO projected part. Have it as a partition function. Needed that thing. From the Hilbert space point of view, it's clear, right? You're projecting something. And that thing came from both these things. Is it clear? Okay, excellent. Okay, excellent. Now, there's one more thing I wanted to say before we move on. I mean, since we've got so far, let me ask the following. Well, at the moment sounds like an academic question. Okay, but let me ask it anyway. The question I'm going to ask is, suppose we had, instead of 4 pairs of fermions, suppose we had 8 pairs of fermions. Okay, could I build a nice modular invariant partition function? 8 pairs, so 16 fermions. Okay, in that case, could I build a nice modular invariant partition function? Okay, so this is the question I'm going to ask. Now let's see what the phases would have become in that case. Everything would have gone through, except that everything would have been doubled. Okay?
So you like 2 copies of the same, like 2 copies of 2A, or 2 copies, not taking a 2A and a 2B. You're saying having 16.
I'm saying having the heterotic string. Well, yeah. Having lots of stuff on one side, more than 8 on one side. Okay, I'm saying this for a reason. We're going to have to put that there. Okay. Okay. In fact, let us first start with 4 copies. Is that easier? Oh, well, let's do 2 copies of these. Let's do 8 of each. Okay. Then each of these guys comes with. So the first 2 guys come with the phase e to the power 2 pi I by 3. And the second comes with the phase e to the power minus 4 pi I by 3. What?
The thing that changed this relative sign was -1. Was one extra factor of I pi.
The thing that changed this, the relative sign between these 2 and these 2, you're saying?
Yes.
Uh-huh.
The factor of I pi.
Uh-huh.
Now that will be 2 I pi.
Exactly. Right. So now, let me just do that. So suppose I pulled out an e to the power 2 pi I by 3 out of this. That's what you're saying. So this is a 1. So this will come now with a factor of minus a relative sign which is just 1 plus 1.
It is 2 pi I.
Exactly. The thing that was I pi becomes 2 pi I. Okay? So what's happening in that case is that there is no relative sign between these guys. Okay? Now I want to show you that in that case what is going to work is, so what we had previously was z00, sorry, right, 0, 0 is what we called it, right, z00 minus z.
Basically, you will not get any help from the phases, so better you have classes.
Exactly. So you will have z00 minus z01, okay? And now what we had was this strange relative minus sign between these 2 terms and those 2 terms. And that's that relative minus sign that was being cured. Okay? So now what we will have is plus z10 and then minus plus z1 1 plus minus, sure, plus minus z11 and the whole thing to the power 8.
So we want to move this up to 12.
What?
But then if we move it up to 12.
If we move it up to 12, we once again need the same minus signs that we wanted, that we had before. Okay? But if we move it up to 16, once again this is the thing that will work. Is this clear? So suppose we were dealing for whatever reason with groups of 16 fermions or groups of 32 fermions, and we wanted to write down some sort of partition function that was modular invariant. Okay? We wanted to write down a partition function that was modular invariant. This is the thing that would do the job. Is that clear? Okay? This is something we're going to come back to in just 10 minutes. What? 8 8 pairs will work if we make it plus. And then there's some overall sign outside. Okay? Okay, and that overall sign.
What happens to the box? I mean, plus, minus, and minus, plus. Previously it was.
This and this?
No, the second and
Yeah, that second. Okay, let's just work it out. Let's just work it out. So, in this case, what are we going to get? The first phase was, what did we have here? We had e to the power pi I by 3, so it's going to become e to the power 2 pi I by 3.
No, you're not talking about top plus 1. You're talking about top minus 1 over top.
Yes.
Ah.
Second and
Ah.
previously it was 4.
This is a good point. This is a good point. Maybe we want.
You put a minus on the first
Maybe we'll. Sorry, I'm sorry. We want a plus here. Thank you. Thank you. Thank you. Thank you. Thank you.
and no minus on the first term?
What? No minus on the first term. Just plus. Yeah. Actually, we want to do the GSO projection. We want to do a GSO projection on these internal oscillators, as we will see in 10 minutes. But there's no help from the ghosts in this case. So the GSO projection comes with a plus. Thank you, Shuman. Yes, absolutely. Yeah, this is the thing where we need. Yeah, something with all pluses, and then a plus minus up here.
So, how can we interpret this in terms of some field theory language? For example, in the earlier case, we had some fermion loop generating a minus sign.
Yeah.
What's the analog here?
As you will see, these oscillators will not be associated with space-time directions in the heterotic string. So there, things that you get by quantizing their zero modes are not associated with space-time spinners. You will see this by the end of this class or the beginning of the next class. Okay? So precisely for that reason, their zero modes have nothing to do with space-time spinners and nothing to do with the spin statistics here. No, the heterotic also has fermions, but you see fermions come from the zero modes. I have to tell you what the heterotic is. Okay. In fact, I'll tell you in 2 minutes, but first just the algebraic point. Okay. So, okay, great. So are we all at the moment satisfied with the modular invariance of the type 2 theories? And do you see that it required, some quite nice things to happen in some coordinated way. These funny phases precisely had to work so as to match the spin statistics theorem in spacetime. It's this, the funny phases were coordinated with the fact that we had minuses for the Ramon sector and pluses for the bosonic sector. And we had, for instance, 16 fermions, so 8 pairs. We would have had to have chosen this. That's the only way of being modular invariant, and we would have violated spacetime spin statistics. Okay. Now, I'm going to come back and work this whole thing out more carefully with the ghosts. Okay, we've worked this out in light cone gauge so far. Okay, you remember we did this in the bosonic string first in light cone gauge, and then more carefully with the ghosts, and made no difference. Same thing's going to happen here. It's going to make no difference. Okay, I'm going to come and show you that because once in your life you should see all these things. Okay, then you forget it, right? You know it works in light cone. It's the same way. But anyway, but before that, I want to move on to one more thing since we started talking about the heterotic string. Let me quickly introduce to you the main idea of the heterotic string, and then we come back and do all these cases more carefully. Okay. Now, the main idea goes this way. So far, what we've done in our course so far, we've studied strings whose left moving. The first thing we did was the bosonic string. Okay, where on the left moving side and the right moving side, we modded out the theory by the conformal algebra. Right? Physical states were only conformal primaries. Anything that was a descendant was null, basically. It was BRST closed. Exactly. BRST exact. Exactly. Okay. Then the next thing we did was to look at the type 2 theory. Okay, or the type 0 theory for the following statement that the distinction is not important. Okay. Oh, by the way, I should have said, sorry. Type 0 modular invariance is unfortunately trivial. Why is it trivial? Because, you see, type 0 modular invariance the type 0 partition function is what people sometimes call the diagonal invariant. It's of the form z00 times z bar 00 plus z01 times z bar 01 and so on. Okay? Firstly, in type 0 there are no funny phases. Why are there no funny phases? From the physical point of view, it's because type 0 theory has no Ramon sectors. No Ramon-Nebuchot sectors. It has Ramon-Ramon sectors and has Nebuchot-Nebuchot sectors, but it has no Ramon-Nebuchot or Nebuchot-Ramon sectors.
Yes.
And therefore no fermions. Okay, so you don't expect funny phases. And then if you work out just, the partition function of the type 0 theory, it's got this left moving times right moving part. So whatever phase you get here cancels.
So then why do you make this distinction between chiral and antichiral? Type 0 theories? Type 0A and 0B theories, there was distinction. A was non-chiral, B was chiral, I guess.
B was chiral. B was chiral because you're doing the same thing on the left and right side.
Yes, but then you have no fermions. It's not dependent on chirality of the fermion, you are saying.
Well, yeah. You get chirality in the sector of forms.
That you can also get, that you will get.
And that you will get, because you have a Ramon-Ramon sector.
Bosonic, still you can have self-dual forms.
Exactly. You see, even though you don't have any fermions, you have Ramon sectors. So, in the Ramon-Ramon sector, either you have states which are in the product of chiral with chiral, or you have states which are in the product of chiral with antichiral. Okay, excellent. Let me show you this more carefully since the question has come up. Let's remind ourselves what the spectrum of the type 0 theory was. Let's take, for instance, type 0B theory. Okay. In type 0B theory, our spectrum was NS plus, NS plus, NS minus, NS minus, R plus, R plus, R minus, R minus. Now, just from the statement, what I said was clear. Because whatever is happening on the left moving sector is also happening on the right moving sector. So, if you've got a Z00, they'll also have a Z0 bar, Z0 bar. And therefore, no matter how funny the phase is, it will cancel. Okay? So, phases play no interesting role in the type 0 sector. Okay? But in the type 0 theory. So, the type 0 theory is much less interesting in the sense that just from the criterion of modular invariance, you could have built it in any dimension. You could have built it in 6. Other things won't work. We could have built it in 6 dimensions or 10 dimensions. But the type 2 theories are more interesting, right? They work in 8 dimensions. Yeah. They're more interesting modular invariant than this dumb diagonal invariant, which you can always build. Is that clear? Okay. Fine. So now let's move. Let's immediately. In 10 minutes, I'm going to have to stop because, yeah, okay, yeah, okay, yeah, because I have an engagement. Okay, okay. Let's quickly give you an introduction to the heterotic theory, and we will see this all in more detail in the next class. Okay. Now, so as I began to tell you, in the bosonic theory, what we did was took the left moving sector and the right moving sector. Both the left moving and the right moving sector were bosonic, but what we really meant by that is that both of them had the structure of a conformal field theory modded out by the conformal algebra. In the superstring, what we had was a superconformal theory modded out by the n equals 1 superconformal algebra. Exactly how that's working, I have to show you, because I have to tell you how the BRST construction is working for that. But you will see that all our states, roughly speaking, have to be, in some old canonical quantization style, have to be like super conformal primaries, annihilated by both the conformal descendants and the superconformal descendants. Okay? But, as you have seen, the whole structure of string theory, in very little does it couple the left moving and the right moving parts. That's so basically only in the zero modes of the bosons. Okay? At least at the local level. Then maybe modular invariance will couple that and so on. But in most ways, the left moving and the right moving part are on their own trip. So something you could wonder about, and we'll discuss this in more, we'll discuss other possibilities in the next class. But something you could wonder about, if you're the slightly crazy kind of physicist, you might wonder about the following. You might wonder, well, what if we took a bosonic string on the left moving side and a superstring on the right moving side? That is, what if we took the left moving side to be modded out by conformal algebra, but the right moving side to be modded out by the superconformal algebra? Why shouldn't that work? Because there's so little crosstalk between the two sides. Why shouldn't that work? Well, if it's got to work, both sides have to have c equals 0. And now at the beginning you think, well, this is a bit crazy, because then the left moving side has to have c equals 26, and the right moving side has to have c equals 15. Right? Because the superstring works when c is 15, because when d is 10, c is 15, because there's one fermion and one boson for each matter field. So you might think, well, that's a bit crazy. But why exactly do we think that's crazy?
The same ghosts on both sides as well.
We don't need the same ghosts on both sides. We'll have to have on the left moving side just the bosonic ghosts, and the right moving side the super conformal ghosts. Because the BRST symmetry on the left moving side will have to be that of the bosonic string theory. The BRST symmetry on the right moving side will have to be that of the superstring theory. Okay? But okay, so if it's got to work, then what we...
There will be nothing like level matching condition or something.
No, there will be a level matching condition in the sense that, once again, your level matching condition is statement that L0 and L0 bar are both 0. Both of them have a contribution like from space-time p squared by 2m.
So you are making them both zeros.
Both 0 or whatever, it doesn't, depending on what you mean by L0. If you, yeah.
What I really wanted to say, that is another place where you need to match from both sides.
But that we will do anyway, because that's just part of the left moving side's condition and the right moving side's condition independently. The fact that L0 is equal to L0 bar anyway follows from the fact that L0 was 0 and L0 bar was 0.
Yes.
It's a deep theorem of mathematics that zeros. Okay. Okay. So. So that was anyway left and right by itself thing. Right? So now look, so suppose we've got a string now moving in physical 10-dimensional space. Go on.
We know tricks to sort of change C, like add a linear dilaton or something, or I don't remember if compactification also does that.
No, compactification doesn't do it. But of course the simplest trick to change C is add more fields, right?
Some internal degrees of freedom.
Exactly. So suppose we want a theory of, you see, the x's. The thing that really couples the two is the zero mode of the x fields. They have to be the same zero modes on both sides. So if the right moving guy was moving in 10 dimensions, there are 10 zero modes. So the left moving guy should also be moving in 10 dimensions. Okay? So the left movers are moving in 10 dimensions, and then you've got 16 central charges to spare. Yes, you need to build up. So the idea might be, let's try to add a C equals 16 conformity theory. Now let's first try experimentally. What is the simplest C equals 16 conformal field theory that we know? We want something that makes sense as a conformal field theory by itself. Why do we want something that makes sense as a conformal field theory by itself? We want something such that it will work up to possible, right. we want something so that, because the other parts are going to work by themselves. So we want this internal part to be a well-defined conformal field theory by itself. For instance, in the sense of modular invariant partition function. The partition function of the 10 bosons and the 10 bosons and fermions, the superstring, has good properties by itself. So then the product of the internal partition function has to be good by itself. Okay? So we want some C equals 16 conformal field theory, which has a nice modular invariant partition function by itself. Can you think of any? Exactly what we just did. Suppose we took a theory of either 16 plus 16 fermions, each of them separately JSO projected, such that the partition function was this. So in this 16 sector, we have both the Nebel-Schwarz and Ramond sector, and we have the JSO projection. Okay? Or we take the set of 32 fermions with one single JSO projection. The two partition functions are either this thing, the whole thing square, or z to the 16 0 0 plus z 0 1 to the 16 plus z 1 0 to the 16 plus minus z 1 1 to the 16.
So this is ASO32 heterotic string?
Yes. So one of them is going to be SO32 and the other one is going to be E8 cross E8. Okay? This is, we've just checked that up to overall phases which we have to check. Overall phases from both the left and the right side, we have to check that working. But up to that overall point, we've just checked that this is a fine partition function by itself. This is a fine partition function by itself. In the next class, I will try to classify all the good partition functions we can get from this point of view. Okay, that give you a nice modular invariant partition function. We'll try to get a classification of those. This is actually closely related to the. Anyway, suppose we do this for a moment. Okay, then then what we have is a left moving side with just the bosonic part, a right moving part with the side with the super part, and at least to the level of partition functions, a modular invariant partition function. Okay? So then we can at least try to make sense of this theorem. Now this is not the only possibility for having partition functions that are modular invariant by themselves. But I want to emphasize one thing, it's not easy. It's not easy to make modular invariant partition functions with only left movers.
So it is in this sense that we have exhausted the list of possible superstring theories? No, I mean in the sense that it's not easy to make...
Exactly. It's not easy to make modular invariant partition functions with only left movers. It's very easy to make it with left movers and right movers. Because one thing to do is to take like that dumb diagonal modular invariant. Okay? But it's not easy to make modular invariant partition functions with only left movers. This is because partition functions that are made only of left movers are analytic functions of tau. Okay? And there is a theorem in mathematics that says every function that is modular invariant, okay, is some functional or some function of a modular invariant and analytic. If you put these two things together, that something is analytic and modular invariant is highly constraining. I don't mean modular covariant, okay? I mean modular invariant. Okay? This is a very constraining thing, and mathematicians have just classified these functions. There's this thing called the psi function, which I'll tell you about a little bit next time, if you're interested. And then there's basically a theorem that tells you that, this function and things you can do with it generate every holomorphic and modular invariant thing. So I said this to say that it's not easy to make things, it's not going to be easy to make things that are modular invariant by themselves with only left moving things. There's another point of view that we should, that I will also tell you about next class, which is the following point of view. You know, as you probably remember, you can take these fermions and bosonize them. Okay? And as you remember, we will review the bosonic. If we let's say we took these 32 fermions, we will get a set of 16 chiral bosons. But now these 16 chiral bosons, when you have 16 chiral bosons, do you remember that one way of thinking of these bosons was from the point of view of a lattice? And do you remember the constraints of modular invariance were nice constraints of the lattice? It was a self-dual, even self-dual lattice. Now, when we studied this before, we studied in the context of, let's say, compactification of the bosonic string. Then there our lattice was made up of the x vector on the left and the x vector on the right. And so the inner product on this lattice was as many pluses as there were minuses. Say we compactified 4 x's, the inner product was plus, 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 minus, 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 minus. On the other hand, here, in this case, our inner product is just entirely pluses, because it's all on the left.
So what's the motivation for wanting to have everything just constrained, of having it just on the left-hand side?
Because we want to take bosonic string on the left and fermionic string on the right, and we want to work in 10 dimensions.
Is there some reason why we don't want to have this nice symmetry between right and left?
Oh, yes. So it's not the most symmetrical thing to do. But we want to do everything we can. Okay? You know, we're just trying to explore whatever we can do. There is another reason, of course. These heterotic strings are less supersymmetric than type 2 strings and were thought to be nearer to phenomenological model building. But that's not, the real motivation is we're trying to explore every construction we can make that will give us a consistent theorem. And as you will see as we go along in the course, all these constructions meet each other through dualities. So if we'd missed one, we would have seen it by doing some sort of space-time duality eventually. Okay, but we want, at the level of trying to construct perturbative, say, graviton scattering amplitudes, we want every one we can construct. Okay, if it doesn't look too symmetrical to us, that may be okay, provided it's consistent. Okay, so now in this case, what we're going to have is that the entire lattice will, I mean, it's clear, right? All these fermions are on one side. So if you do this bosonization, everything is coming from the left movers. All the x fields are left moving. And so the inner product will be just 32 pluses and 0 minuses. So it's going to be a Euclidean even self-dual lattice. Now, making Lorentzian, especially with equal dimensions, even self-dual lattice is not hard. Roughly speaking, because you can make modular diagonal invariants. But making Euclidean even self-dual lattices is very hard. For the same reason, because this is equivalent to making some sort of partition function that is both modular invariant and holomorphic. Okay? So from another point of view also, mathematicians have studied this issue. What is the set of all Euclidean even self-dual partition lattices? Both these things have been classified. So we could use either of them to answer our question. And we look at it from both points of view next time to get a full set of things we can do. Okay, so that's it for now.